Okay, and this result will, later you'll see many results of this kind. So yeah, this is basically completeness of, right. You will see many results of this kind. Okay, so completeness of this under the uniform metric, let's start writing it as this, and you will see why we put infinity there. But let's say, what's the definition? So number one definition, uh, right. I mean, yeah, definition will be that you take f and g, then this thing is equal to supremum of this. And this is what you can expect. And you already know it, I think. So this is one of the natural metrics to put, if you are in these kind of function spaces and so on. So you sort of, yeah, you'll see this is a natural definition. So this is the definition. And one of the facts which I'll be using is just simpler to prove. And at one point I had told the idea, but yeah, one of the facts is this. And if you consider this thing, which is right like this, and this is simply the collection of all bounded functions. So this thing is collection of all bounded. So no longer we are saying continuous, but we're just saying that it is bounded. Yeah? Collection of all bounded functions. Functions just means it's going to R. Okay? And yeah, then the fact is that, so maybe this is just a definition. So here, what are the obvious homeworks? I mean, you have to check that this is a metric space, right? You have to show that it satisfies all the properties of a metric space. So all those things are implicitly there. So that's the work you have to put in. And then this thing again, we are putting the same metric, and it makes sense because it's bounded. So the distance will be finite. So this, okay? This is complete. Okay, this I will be using. Okay, and actually you may say, now this is another theorem. Right. The point is that even if you don't know this theorem, it's not a problem, because what we will prove actually is that this is some sort of a closed set, and the heart of the matter will be there. Completeness will follow yeah. So this is fact. But if you know it, then you can complete it. You can sort of connect all the ideas and together. Then you can say it's that this is a complete metric space. Can it be avoided? So if I just take a Cauchy sequence of continuous functions, I can show that it converges. Yeah, actually you don't need it. Yeah, actually you don't, I mean, yeah, but actually you don't need it, but let me still keep it there. Okay? Yeah. Okay. So what else do I want? Nothing. Now you can just try to prove this result. Okay. Before getting into the proof, let me see if I want to say something. Yeah, like this is a very concrete. This is a very concrete question. Okay, it's a very concrete question. So yeah, so let me first maybe write this thing. Hmm. Yeah, let me write this thing because that will be nice. So let's say, so maybe I'll call this interpretation. An interpretation. It's going to be an interpretation of convergence in, yeah, so I'll just call this thing B. Okay. So these are just bounded functions. I'm not saying anything about continuity, but now I'm going to make a comment on this space because that will also apply to this C0, 1, because obviously C0, 1 sits inside this space. Yeah. But this is going to be nice. Interpretation of convergence in B. Yeah. So what am I saying? So let's say that if I give you this sequence of functions. Now sequences of functions is obviously very important topic. This is just that, nothing else. Let's say that it converges to F, obviously in B. Okay, so everything is happening in B. What this is saying is that Fn converges to F. That's usually you say is uniformly converging, right? That's the thing. So yeah, so that's already there. That's what you usually say, that it's uniformly convergent. Okay, but even if you don't know the term, that's not my point. My point is something slightly different. What is my point? Yeah, I want to say something about exchange of limits, a limit, and yeah, because that's interesting. That apparently interests a lot of people who come from a different taste sometimes. So I want to just put that out and then leave that for you to prove and think. Okay, so you look at this thing. Okay, just this, and right, just look at this thing, and then you look at this thing. Yeah, this makes sense, right? This expression makes sense. This limit yeah, so you have fixed a point x naught. You can draw a picture, right? You fix a point x naught, and then you have this thing. If you had continuity, then you can just replace this by fn x naught, but I'm not giving that at the moment. I'm just writing it like this. Okay. So you have this, and then basically for every n, you get a number, right? This will just be a number. It's just a number, right? Not a function. And then you can take its limit. It may not exist, but you can at least consider the expression. So that's that. Finally, it's just a number. Now, okay. So now you just consider this x. Just reverse the order. and you know what I am going to say. And then you take limit x tend to x naught. Okay. Now, of course, you already know that this is the function fx, right? Because that's already given to you here, right? Right. If so, obviously, if this sequence of functions is converging to f in this metric, then you write what that means, and that will obviously imply that for every point also it converges to f, same f. So this is basically fx. So since it is fx, let me just write here also it is fx. I'll still maintain that expression because it kind of looks good. The order is reversed. Uh, and my claim is that these two are equal. Okay, and this is the claim. See, this is not a simple question. This is maybe not so simple, right? But at least it can be easily formulated, right? It can at least be easily formulated, but it is not simple. This answering this question, which is so nicely formulated, actually subsumes this. Proving this will actually prove this thing, so it's not so easy. But I mean, yeah, well, but you should meditate over this. I mean, you should think about this later. Yeah. I mean, so of course, here you have to assume something, which is to say that maybe you can assume that limit fn x going to x naught exists, for all. Yeah, so you assume this so that this thing exists, and then you can look at this. Okay, so if you would like to draw a picture, so what is happening is for every n, you are computing this limit, so you're getting these numbers, and basically you're asking where will these numbers converge. Okay, and the answer is that, well, you look at these functions fn, right, and you converge them, right? You take the limit, you look at f, right, and then you for f you compute this limit, and that's where these numbers will converge. It's such a natural state, but it happens when you have uniform continuity. I mean, otherwise it doesn't seem to happen. This will obviously not imply uniform continuity that you can sort of understand, but yeah, uniform continuity implies. So uniform continuity is a very nice statement. Yeah? So you can, yeah. But let's get back to our main result, which is this thing. And this you can find in Rudin, Baby Rudin, Principles of Mathematical Analysis, in chapter of sequences of functions. Most of things that I said today, you can find, but with different language, different notations, and yeah, sometimes they have different goals, and so. All right, but then let's quickly finish it so that we can just rest uh, and think. What I'm now just saying is that now you just take a sequence of continuous functions. Now you assume everything is continuous, and it converges to f. Okay, these are all continuous functions. Okay, and well, you want to show that f is continuous. That's all, right? Or I mean, yeah. First I will show this. First I will just show this. Okay, that this suppose this converges to f, and then I will show that f is continuous, right? So that's what it means, right? For it to be closed, I'll show that it is closed. Okay, so these are continuous, and this is converging, right? And I want to show that f is continuous, right? limit is also continuous. Obviously, you notice it's converging under this norm, under this metric. That's important. So show f is continuous. So how do you show this? Well, just use the definition. So what is the definition? Well, you have to fix a point, and then you want to you just try to estimate this difference. Am I correct? Right? You will try to estimate this difference, right? Fix the point and estimate this difference where t tends to x naught and try to show this goes to 0. That's all, right? So you just try to estimate this. So how would you do? Well, you can just, no, it's just a matter of writing or maybe also drawing a little bit. You consider x naught and you consider t. And then you have considered these 2 points. I mean, this is f of x naught, and f of t. And you want to show that this distance, no, you want to show that the vertical distance becomes small, right? You want to show that this distance becomes small, right? I mean, yeah, it's better to do in metric spaces actually, as you don't have to think about so much, so many not important things like vertical and so on. But anyways, I mean, in this case, vertical and so on is not important, right? But anyways, this is fine. So how do you take assistance? You take assistance of these things, right? These f's and so on. So you can say, okay, uh, uh, let's take an f which is really close, right? So suppose just take an fn which is really close. So this is f. Take an fn which is very close to it. So how do you make it work? You take an fn which is really close to it and you do this, right? Consider, but then you have to adjust, of course, and so you have to write it like this. So you consider this, right? You see what happens is that this distance will become very small because, right? So you're taking some fn and fn in general is close, right? And that close you can write if you think about this metric, right? So fn is this, is close. So for all t, right? So what I'm saying is that fn minus f, let's say less than some epsilon. You can arrange for such an n, right? And this means for all x it is true, for all t it is true. But the problem is now that this x naught ke liye you want an x naught, fn x naught, right? You don't want right? You want an x naught, correct or not, right? So that's why, I mean, this is equal. I've not done anything. Yeah. So maybe I'll just, yeah. Sorry, not done anything. So again, just for the same, for the same reasons, right? You can just add a fn x naught and see if it helps, and subtract fn x naught, right? So what advantage does all this give you? This is the fundamental things which you are doing. It's not just a trick. It's going to invoke the triangle inequality. It's a fundamental thing. This is small, right? This is small. That is 0. Yeah, this is small, right? And this is small, right? So why is this small? This is small because of continuity of fn. Now that's the catch, right? That these are continuous. So you have a continuous thing which is very close to it, so it also makes it continuous. That's the point. And now you just use triangle inequality, put the mod, use triangle inequality on those pieces, and what do you get? You get that for this t, this thing is less than epsilon. That is because of this condition. And you can pick a delta so that this thing is less than epsilon, right? That's a continuity. And this is less than epsilon for the same thing. Now I have left a few holes in this proof. Okay, it's like, yeah, so given yeah, there is some problem, there are some problems here, but roughly you see that it's less than 3 epsilon, so you're done. Okay, now you should try to fill in the gaps. Basically, try to go about the proof and see. Yeah, but you understand the goal. Once you understand this clearly, then it's very easy. That you want this thing to become small, and so you want a delta, right? So yeah, so for that, so you want a delta so that it's small, right? And but then you see, you want to make this epsilon small, you find you get an n. Now for that Fn, you have to find a delta so that this thing becomes small, right? But you will get a delta for the epsilon finally, right? And that will not, that will be just depending on epsilon. I mean, it will depend on the Fn, but it is not, in the end, you get a delta for which this happens, right? And yeah, so that for all t minus x naught less than delta, this is basically f is getting replaced by Fn. That's the thing. So that's it. You should still write the proof and think about the proof. And yeah, so what have we shown here, right? We have just shown that this C0, 1 is closed in B, right? Because I said that if this converges to some f, right? Yeah, under this converges to some, obviously this f is also going to be bounded, no doubt, if this converges in this way. You can show that, right? Then this f is actually inside, is actually also continuous. So it's inside this set, is inside this. That's a good thing, right? So it means it's closed. And then you know that a closed subset of a complete, closed, subspace of a complete space is also complete. So from there you can conclude that it is complete, right? So I've invoked the completeness of this, but actually that's not really needed, right? Because you can, I mean, yeah, what you can just do is you can just take a Cauchy sequence, and just instead of taking convergence, you can just take a Cauchy sequence and then show that it converges to some function, and then show that that function is continuous. That will just show everything, right? You don't need to go to that B, right? But this is just nice, and sometimes this is very essential. Sometimes, if you want to show that some space is complete, and you can put it inside some space which is complete, then you could just have to show that it is closed. Sometimes that's useful, because yeah. So I mean, that's all I would like to say today, right? Let's not make it longer and longer, because I think it's not very useful to. So we have said a few things. I've given you the reference. You can read from Rudin, and obviously, if you want more, not, I would not say advanced, but more, it is a different goal. I mean, the Monkrus has a different goal. So you can also read Monkrus chapter, which is there. I'll tell you the section. You can just read it. Chapter 7, section 43. That's the easiest way, because there are many other things in this book. So you can read chapter 7. So this is section 43, Monkrus topology, James Monkrus. Also, an Indian edition is there. You should have this book with you. It's going to be, it's a very amazing book, no doubt. I mean, I'm no one to say that it's a time tested. This, and of course, Rudin's also, Rudin, Walter Rudin. Principles, first book, the Principles. Here also, you can look at the chapter on sequences and series of functions. I think it's chapter 9, but yeah, you should look at this chapter. If you do these things actively, it's very nice. All the other things which you have learned will get revised if you want such a term in this, if you work out the things actively and think about them. And even a lot of the, we think, okay, it's like tricks, and so we'll solve different kinds of problems and it will happen. Yes, of course, but if you also work these things out, there are problems hidden in these. Mathematics, a certain kind, as works in a certain way now, especially more and more as you go higher, that things can be generalized and put into a place where other things follow. So yeah, I mean, that's but yeah, point is that if you work these things out, it's very important. You should do it. Okay. So you can just divide some time. Maybe you can tell yourself, okay, one day maybe I'll read this section. You don't have to understand every line of it. That's not important at this level. But it's a certain thing that if you just put yourself through it and do it, you will see. And you may feel that you're not understanding, but I mean, yeah, if just the effort has to be put in. Okay, and yeah. So you should like maybe put one day and read this, divide the time and so on, and then read this patient. Okay. And see. I mean, there are problems hidden in this small example, small topology, small, then you connect, and it's nice, yeah. And of course, yeah. So you okay. So that's it today. And as I said, we'll meet on Sunday. We'll try to solve some jam questions. And as Aryan was saying, there were some questions. So maybe the idea is to also just surprise ourselves with some mathematics. Not this is of course there, but we can also do that thing sometimes. And we'll see how. All right. So that's it. I think stop
So,
today.
Sunday 12:30, right, sir?
Yes, Sunday 12:30 is fine, right? I think
Yes.
we can do
Yeah.
that. Yeah. And Saturday,
Yes. Yes.
this Saturday, let's not do. Let's
Okay.
call it off and give ourselves time and yeah, do these things.
Yes.
Okay.
Okay. Yes.
Vaishnavi, is that fine?
Okay.
Yeah.
Okay, okay, sir.
Is that okay? Yeah. All right then. Yeah, that's it. Good night. Think about this. Bye.